Hi, this is lesson 7 of solar energy application. We are still in the topic of solar radiation. This is part 6 of solar radiation. I think we have two more lessons on solar radiation, and then we'll start solar thermal, and after that solar photovoltaic, and finally other applications. Okay. This was our textbook, just for a reminder. Topics of the previous session, if we have a short look, included a spectral distribution of extraterrestrial radiation, atmospheric attenuation of solar radiation, data resources, and we just spoke about one of the solar radiation models, which was the clear sky model. And today we will learn about other solar radiation models. Just for a reminder, solar radiation models can be classified based on different categories. For example, based on the type of model, which may be linear or nonlinear models, based on the number of input parameters, which may be 1 to 4 or more even, and based on the type of input, which may include different parameters like the sunshine, duration, temperature, relative humidity, latitude, altitude, or height above the sea level, cloud cover, transmittance, and pressure, and maybe other parameters. Last week we discussed about one of the models, which is a very simple model named clear sky model. You may remember that this model is based on the assumption that there is no clouds in the sky, and if there is such a situation, you may use the clear sky model. But estimation of the solar radiation extends beyond the clear sky model. As you can see here, radiation data are the best source of information for estimating average incident solar radiation. It means by radiation data, it means as I can understand, the measured data. Actually, it may be better to say measured radiation data are the best source of information. But as you can see, lack of these data from nearby locations of similar climate, it is possible to use empirical relationships to estimate radiation from hours of sunshine or cloudiness. Data on average hours of sunshine or average percentage of possible sunshine hours are widely available from many hundreds of stations in many countries and are usually based on the data taken with Campbell-Stock instruments. You can see such data, for example, for the average hours per day of sunshine for different locations from Hong Kong to Madison, Wisconsin, in different months of the year in your book table 271. Okay, so in summary, there are a lot of stations in the world where sunshine hours is measured by generally very old Campbell-Stock instruments. There are more new instruments as well. This is one of the devices, a picture from Campbell device, which is used for measuring hours of sunshine. So as you can see here, data on average hours of sunshine are widely available in many weather stations. Even for developing countries, these data are generally available and can be found from metadata sources. You can see, for example, here the same example for 3 cities in Iraq, for example in Baghdad, Mosul, and Rutba. As you can see, for example, for Baghdad, in the month of July, you have 12.3 hours of sunshine. Please note that this is not the day length, because day length, for example, in July may be more than 12 hours. It may be 13 or I don't know, maybe 14. You can calculate it by the formula which I discussed about them before. But 12.3 here means that you have 12.3 hours of bright sunshine in Baghdad in the month of July, and this is different from the day length and always less than the day length. Okay, and you can see the same for different months of the year, and the same data you can find in many from many weather stations in the world. First models for modeling solar radiation express the relationship between solar radiation and sunshine duration, because the sunshine duration, as I explained just now, are available generally for most parts of the world. And Angstrom was the first who proposed the theoretical model for estimating global solar radiation based on the sunshine duration. You can see here at the bottom of the page the original paper by Angstrom, which goes back to April 1924. This is very old paper, which is solar and terrestrial. Terrestrial, you may remember that terrestrial is on the Earth, or considering the effect of atmosphere. Report to the International Commission for Solar Research, and the first model, this is actually the first published model for modeling the solar radiation, and it goes to 1924 and presented by Angstrom. This is the Angstrom original model. The original Angstrom type regression equation related monthly average daily radiation, which is H bar, to clear day radiation, which is H bar C, at the location in question, an average fraction of possible sunshine hours. This is N bar over N, as I explained before. N bar is sunshine hours, N is day length. The bar here shows the average for the month. For example, N bar, capital N bar here, means that this is the average day length for the month of, for example, July, June, or other. Actually, a basic difficulty with this equation, as you can see here, is the ambiguity of the term N over N, and especially H bar C. And this made other researchers, most important was Page in 1964, that it made a change on the original Angstrom equation, and a change H bar C to H bar 0, which is very simply can be calculated, and as you remember is the extraterrestrial radiation, which may be calculated from the formula or graphs or tables I showed to you in the last session, or I don't remember, maybe the session before that. The term H bar over H bar 0 is termed the monthly average clearness index. Remember this term, as we will use it later today, and will be used frequently in later section and chapters. So actually we use this equation, and the original Angstrom equation is not used anymore. In this equation, the parameters, if repeat once more, H bar is the monthly average daily radiation on a horizontal surface. Please note that this is only for the horizontal surface. The other thing that you should notice that this is monthly average daily radiation. When we say monthly average daily radiation, we mean the daily radiation. So H bar is for 1 day, but is the average for the month of on the question. For example, for any month, any day in the month of July. H bar 0 is the same, but extraterrestrial radiation on the horizontal surface, and if you remember, we can find it from equation 110.3 for the average day of the month, because you should substitute a value for small n in this equation, and if you are using if you are calculating the monthly average radiation, then you should put a value for a small n. Which value should be substituted? The average day of the month. We had a table for the average day of the month, or table 110.1 or figure 110.1. By either of these three methods you can calculate H bar 0. Small n is the monthly average daily hours of bright sunshine, generally from method data sources. It can be calculated. Capital M bar is the day length. If you remember, we had formulas for that, or figure. And finally, A and B are empirical constants. Generally, in practice, either you have A and B for the location in question. For example, I give you A and B for a specific location, for example, Cairo in Egypt, and then ask you to calculate H bar for that location. The other case is the case where you have actually you don't have a and b for a specific location, so you should have n bar over n and h bar over h bar 0 for that location for different months of the year, and then you can fit an equation like this to the experimental data points to find a and b. I explained it here. For example, suppose that you have the values in a tabulated form as the one you can see here. The first is n bar from weather data or measurement. Capital M bar can be calculated by calculation 1611. H bar from weather data or measurement. H bar 0 from equation 110.3 or table 110.1 or even figure 110.1. Then you can calculate n bar over n bar and h bar over h0 bar. Then you can show the data point in a curve like this. These points, as you can see here, are measured data as per data table on the left, and then by any method, by your scientific calculator, by Excel or any other method, you can fit a curve or line to the data points. In this way, A and B can be calculated. This is also possible even with a simple scientific calculator. By the regression mode of the calculator, you can find A and B. You may use Excel or any other software. So, if A and B are to be calculated for any specific location, you should do the way I showed you here. Many researchers did the same for many locations, even they fit different equations, for example a polynomial to the data points, but in general h over h0 is a specific function of n over n. For example, you can see here different references. If you want to know exact title or reference, you may I refer you to this paper. You can use a complete table there, and you can see that different researchers, for example, for Amman in Jordan, this specific researcher, for example, Azad, in 1990, calculated A and B for that location. The method they used is the same that I explained here. Other data inputs in addition to the sunshine hours may be used. For example, it may be a function of relative humidity in addition to the parameter n over n parameter, or even temperature. Even the shape of the equation may be different. For example, you can see here that this is another form of the equation. For example, the latitude of the location, the elevation of the location, and n over n may be used to calculate A and B. Okay, the next question is, okay, if I can fit different forms of the equation to the data points, which is the best one? In order to validate the model, there are different statistical test methods. Statistical test method is an important issue for the accuracy, goodness of fit, and validation of the regression models. The statistical methods have been widely used by researchers to control the performance of solar radiation regression models. Among different statistical models, I explained and presented the formulas for different ones, as you can see here. The first very important one is the coefficient of determination, which is shown here. It can be shown, as you can see, by the difference between Hi, which is the calculated solar radiation. By calculated, it means calculation by the formula, minus Hm, which is the measured value to the power of 2, over Hm, which is the measured value, minus the Hm bar, which is the average value of the measured value. As you can see, the R2 value tests the linearity between the measured and estimated values, and the model is more representative or better when R2 is closer to 1. Other very important estimation tool is relative percent error, which is simply Hi, which is, as you may remember here, the calculated one by your formula minus the measured one divided by the measured. And as you can see here, the E value is a measure of agreement between the measured and calculated data. It takes negative and positive values and stands for underestimation or overestimation of your formula in comparison to the experimental data. For example, if the value is positive, then it shows that your formula overestimates the solar radiation, or the same in reverse for the negative value of E. Other parameter which you may use, a mean absolute percentage of error, which is shown here. MBE is another parameter, and the definition you can see here. Mean absolute error is shown here. And finally, RMSE or root mean square error is shown here. If you want to know more about these different model validation tools, you are referred to the paper shown at the bottom of the page. Solar radiation data are available for different parts. This table I showed you before. There are also other tables, as you can see here, for different regions. For example, this is for Baghdad, this is for Mosul, and here you can see the reference for these data. If you want to know more about the solar radiation models, you can see this paper, which is a very good paper, and also there are a lot of other papers who reviewed solar radiation models. Another very interesting and approximately recent method for solar radiation modeling is artificial neural network. Artificial neural network is one of the machine learning methods. There are other machine learning methods, fuzzy logics and others. Artificial neural network is one of them, which made a lot of progress in different areas, including its application in solar radiation modeling. As you can see, some inputs are used for the artificial neural network model to calculate or estimate the global solar radiation. Actually, the main benefit of ANN or artificial neural network is for the locations where data are lacking or missing, or there isn't adequate data point for other models or regression models. For example, you can see that maximum temperature, minimum temperature, and extraterrestrial radiation may be used in this model, for example, to estimate the global solar radiation. While, for example, solar radiation, relative humidity, and sunshine hours even may not be available in meteo station, but it can be said that 100% maximum and minimum temperature are available in different parts of the world in the weather stations, in meteorological stations, for example, in the airports or anywhere else. Extraterrestrial radiation can also be calculated by formula, and there is no measurement required for that. So if you can have a model to calculate or estimate the global solar radiation just based on these parameters, it will be very useful for the locations where data are missing. Here you can see the prediction methodology. Generally, a selection is made of input and output data. What input you have, what output you need. Divide data into training and testing sets. So for example, if you have 1000 testing data, you may divide them into training and testing sets by part of the data. For example, 1/3 of the data may be used to train the model, and then you may use other 2/3 of data for testing. Develop ANN model, because there are a lot of the ANN models. Selection and training parameters, training and calculation of error, and finally calculation. If you want to know more about that, because it's not our business in this course to discuss about artificial neural network technique, but these are the papers which you may refer to them. Even this paper at the bottom is especially for Baghdad, Iraq. As you can see, neural network based global solar radiation estimating using limited meteorological data for Baghdad. By limited meteorological data, the authors mean that we are using minimum data, or we are using the method for a location where many data are missing. This is a very interesting topic actually, because you know it is a new topic, and much work can be done on that. Okay, the next method of calculating solar radiation which we will use from now on in this course is Clearness Index method. Actually, it is a very good and simple method, and we will use this method further on for our calculation. Clearness Index, you may remember from maybe some slides back, I told you that we will come back to it. Suppose that this area here to here is the atmosphere, Earth atmosphere. You may remember that the solar radiation at the top edge of the atmosphere is named extraterrestrial solar radiation, and the radiation on the Earth is named terrestrial solar radiation. Clearness Index, in simple terms, is the ratio of terrestrial solar radiation to extraterrestrial solar radiation. Once more, Clearness Index is the ratio of terrestrial solar radiation or radiation on the Earth's surface to extraterrestrial solar radiation or the radiation at the top edge of the atmosphere. You can simply say that the value is less than 1 because terrestrial solar radiation is less than the extraterrestrial radiation, because part of the solar radiation is decreased due to the atmosphere. You may remember that there are two mechanisms, absorption and scattering, and we discussed about them last week. So the Clearness Index in some way can show you the cloudiness of the sky in addition to other molecules or dust, for example, or anything else which may exist in the atmosphere. But neglecting them, actually, Clearness Index simply can show you it is simply higher in the, for example, summer months, and will be less in the winter months. Okay. Section 2.9 of your book discuss about the distribution of clear and cloudy days and hours, which is the topic of Clearness Index. But as you can see here, 3 types of Clearness Index is defined, because when you say it is the ratio of solar radiation on Earth to the solar radiation at the top of the atmosphere, one may ask you, okay, but at which time of the day, at which, for example, time of the year? Based on this, and in order to answer this question, 3 types of Clearness Index is defined, as you can see here. The first is monthly average Clearness Index, where Clearness Index is shown by capital K bar T, and it's the ratio of the monthly average daily clearness index to the monthly average the ratio of monthly average solar irradiation on the Earth to the monthly average daily solar radiation outside the atmosphere for the month, average for the month. The other type of Clearness Index is the daily average Clearness Index. Daily average Clearness Index is defined for any specific day of the month. So here, as you can see, there is no bar over H0 and KT, and here H is the daily daily terrestrial radiation on the Earth, and H0 is daily extraterrestrial radiation on the Earth for any specific day. In the same way, hourly Clearness Index can be defined, which, as you can see here, is the hourly irradiation on the Earth to the hourly extraterrestrial radiation. You may remember that we have formula for I0 and H0 from chapter 1 of the book. Clearness Index values, generally the monthly average daily values, are tabulated in different references, and here you can see, for example, this is the appendix of the textbook, and you can see here, for example, for Cairo in Egypt, the KT value, KT bar value for the month of July, where we are, is 0.67. So this means that in this formula, K bar T for Cairo in July is 0.67. So the ratio of the radiation on the Earth to the radiation outside the atmosphere for the month of July for Cairo is 0.7. So if you have K bar T and you have this also by calculation or from chapter 1, then you can simply find H bar. This is generally, again here there are two ways possible. The first is the case, two cases are possible actually. The first case is where you don't have KT and want to find KT for any specific location. Okay, let me explain on this. For example, you want to calculate KT for any specific day of the year for a specific location. Okay, you can measure H for that location. You can calculate H0 for that location. Please note that I told measure H, calculate H0, because H0 is calculated from the formula, H is measured. Then by dividing these two, you can find KT. And if you repeat the same for different days of the month, finally you can find, for example, K bar T. And the second case is when you have KT for any location and want to find H for that location, which is the case for us in this course generally. The first case is when you are doing a research, for example, in your master course thesis. This is one of the interesting topics which you may think about, that the first case that I explained. Okay, the second case I told you is when you have KT for any specific location. H0, as I told you before, can be calculated simply by the formulas from chapter 1, and then multiplying these together you can find H for that specific location. Let's have an example for this, and I'm yes, the topic here shows what we are going to discuss: monthly average clearness index for Kirkuk in Iraq. Using the data for monthly average clearness index in Kirkuk, calculate the monthly average irradiation in this city on a horizontal surface for the month of July. So the question is, please note, up to this point, for example, in chapter 1, we were only able to calculate, for example, in Kirkuk, for example, the extraterrestrial radiation in July. Now we are one step ahead. Okay, we are one step forward, and we are able to calculate the real terrestrial radiation on any month, on any location, if you have the clearness index for that location. So in this example, we want to calculate the irradiation on the Earth for the city mentioned in the month of July. Okay, this is the steps you should follow. Step 1, find the latitude of Kirkuk, which is 35.5. I just googled it and found that the latitude for Kirkuk is 35.5. Okay. Step 2, find the extraterrestrial radiation for July using either equation 110.3 for the average day of the month, or figure 110.1, or table 110.1. For the sake of simplicity, I used the table for solving this example. You can do other ways also. Okay, if you remember, the table shows here the latitude of the location, and these are the months. The latitude of Kirkuk is 35, approximately 35.5, but we can neglect it. And the month in question, under question, is July, so you can see here that it is 40.6. What does it mean? It means that neglecting the atmospheric effect in each day in the month of July in Kirkuk, you have 40.6 megajoule per square meter of radiation. But the point is that you will not the Earth will not, this whole radiation will not reach the Earth, because there are atmosphere and you cannot neglect it. So the next step is to find the monthly average clearness index for the city in question from trusted resources. By trusted resource, I mean, for example, resources or references that you can trust on the value. And based on the data from below reference, I found a reference here. As you can see, you may go to this paper for more detail, but you can see here that it has the mean monthly meteorological parameters for Kirkuk station during the period shown here, and you can see here that it is KT. The table shows more parameters, but I just put here part of the paper table. And you can see here that for July, KT value for Kirkuk is 0.57. So the next step, step 4, is use equation 291. This was equation 291, if we remember. Okay, we want to calculate H bar. You have KT now for Kirkuk, you have H0, so it's enough just to multiply them. Okay, H bar is KT multiplied by H0. KT is 0.57. H0 from table is 40.6. So H bar will be 23 megajoule per square meter, and this is the horizontal irradiation in Kirkuk in the month of July per day from sunrise to sunset. So if, for example, you have a horizontal surface in Kirkuk with the area of 10 square meter, daily solar irradiation for this month will be 23 multiplied by 10, which is 231 megajoule. Sorry, this should be deleted because we multiplied by the area, so this should be deleted. Megajoule is correct. Okay. Okay, now 2 other questions remained. Please note, because these are very important for understanding the whole procedure. The first, what is the share of diffuse and direct irradiation? Because the total, as you can see here, is 23 megajoule per square meter. What is the share of diffuse? What is the share of the direct radiation? The second, what will be the irradiation on a surface which is not horizontal? Because this is the irradiation on a horizontal surface. For example, suppose that you have a solar panel in Kirkuk at a slope of, for example, 35 degrees. Then what will be the solar radiation on that surface? This will be answered in the next lesson. Summary: in this lesson, some new techniques for solar energy modeling, including linear models, nonlinear models, KT model, were introduced. A short introduction was made to the artificial neural network and its application in solar radiation modeling. In the next lessons, KT method will be continued. Models for diffuse and direct radiation will be introduced to enable you to calculate the share of diffuse and direct radiation, and we will see how to calculate terrestrial irradiation or irradiance on an inclined surface. And this is the end of lesson 7. Thank you for being with me. Take care. Bye.